Welcome to The Explainer. So today we're talking about something pretty incredible, a brand new class of materials. Materials that are literally being built atom by atom to solve some of the biggest challenges on the planet.
You know, we're facing some enormous challenges. I mean, just think about it. One of the biggest has to be the sheer amount of carbon dioxide we keep pumping into our atmosphere. It's a huge problem, and it's going to need some seriously innovative solutions. And it's not just CO2. At the very same time, we're desperately trying to figure out how to clean up our planet's water, to get rid of all the dangerous pollutants and bacteria that are threatening, well, everything, ecosystems and our own health.
So what if the solution wasn't something we just find, out in nature? What if it's something we actually built? I mean, from the ground up? Well, that's exactly what scientists are doing right now. They're designing and constructing this totally revolutionary new class of materials.
Okay, so let's dive right in. And you gotta understand, this isn't about discovering some new rock or something. This is about inventing materials, right from the atomic level up. All right, they're called metal organic frameworks, or you'll hear them called MUFs for short. So what are they? Well, at the very core, they're these super-ordered crystalline structures, and they're made by linking just two basic parts together.
The best way to think about it is like molecular Legos. Seriously, you've got these metal clusters that act like the joints, right? The connecting pieces. And then you have these long organic molecules that are like the struts, the long bricks that link everything together. And here's the cool part. Just by swapping out these basic building blocks, scientists can build a practically infinite number of different, super-ordered crystalline frameworks.
And this totally brilliant way of building things, this molecular architecture, it leads to one truly astonishing property. Get this, an absolutely incredible amount of internal empty space.
Right, so this unique structure is what gives MOFs their superpower, and that superpower is extreme porosity. We are talking about empty space on a scale that is, honestly, kind of hard to wrap your head around.
How much? Up to 90%. Let that sink in. Some of these materials are almost entirely empty space. That makes them the most porous materials ever created. They're basically crystal sponges, but on a molecular level.
So all that empty space means they have an enormous internal surface area. Here's a crazy way to picture it. If you could somehow unfold a piece of a moth that was just the size of a sugar cube, its surface area would be big enough to cover an entire football field. It's wild.
And it gets even cooler, because these things aren't just rigid cages. Nope, some of them are dynamic, they're flexible, they can literally breathe in response to what's around them. Opening up their pores to let certain molecules in and then closing back down to hold them tight.
And this graph, this really shows you just how effective they are. See that super steep curve on the left? What that's telling you is that even at really low pressures, when there aren't a lot of gas molecules floating around, these MOFs act like total super sponges. They just soak up huge amounts of gas really, really fast.
Okay, so we have these designer crystal sponges. The big question, of course, is how do we actually use them? How can they help us tackle those huge problems we talked about at the beginning? Well, for water purification, they're incredibly versatile. You can design them to take out harmful bacteria in a bunch of different ways. For one, they can be made to slowly release metal ions that kill bacteria. Or they can generate these destructive molecules called reactive oxygen species. Or, and this is my favorite, they can be designed to physically tear the bacteria apart just on contact. Brutal, but effective.
And what about CO2? Well, when it comes to carbon dioxide, these frameworks aren't just traps, they're transformers. You can build them with these special active sites that don't just capture the CO2 molecules, they also act as catalysts, helping to convert that nasty pollutant into valuable chemicals, stuff we can actually use. So you're not just storing a problem, you're turning it into a solution.
Okay, but hold on. Having a powerful new tool like this is one thing, but using it sustainably, that's a whole other ballgame. I mean, it doesn't do much good to solve one environmental problem if you create another one while you're at it, right? It's not just about what you make, but how you make it.
And yeah, that's been a key challenge. A lot of the early ways of making MOFs, well, they weren't very green at all. They often needed a ton of energy, used some pretty toxic solvents, and took forever, sometimes hours or even days.
But the whole field is evolving, and fast. Researchers are now coming up with way greener methods to make these things. Methods that use way less energy, safer stuff like water, or, get this, sometimes no solvents at all. They can just grind the starting powders together. It's awesome. They're really trying to make the solution as green as the problems it's supposed to solve.
You know, this whole approach, it's really a whole new field of science. One of its pioneers, Professor Omar Yaghi, he calls it reticular chemistry, which is basically the art and science of building with molecular blocks.
And this is really the most important thing to take away from all of this. MOFs represent a huge shift in thinking. We're moving away from just discovering materials that happen to exist to actually inventing them. For pretty much the first time, scientists can look at a problem and say, okay, what kind of material do we need to fix this? And then they can go and build it from scratch, atom by atom, to do exactly that job.
I mean, this breakthrough just blows the doors open to a world of possibilities. We've been talking about CO2 and water, but think about medicine, energy storage, you name it. Which really leaves us with one final, pretty provocative thought. Now that we have this incredible power, this ability to build materials to solve specific problems, what problem should we solve next?